Today's set of notes is about radiation, and we're going to be discussing what radiation is and the different types of radiation. So we may have heard the word before, and we may have heard it used with mutations, and we may have heard it used with Spider-Man or different superheroes, or we may have heard it in terms of cancer. But we're going to look at what radiation is from a chemistry standpoint. And the truth is, we're exposed to small amounts of radiation every day. It's just when we're exposed to large amount of radiation when it becomes dangerous and it could cause mutations in our cells. So our first question is, what is radiation? So the definition is, radiation is particles or rays that come from radioactive material. So from that, we should naturally have another question. What makes material radioactive? So that leads us into this question. And the answer to that is that atoms that are unstable are radioactive and they release radiation to become stable. So we have learned about how neutrons can affect whether an atom is stable or unstable. And by either losing neutrons or gaining neutrons, that atom can find stability. So atoms are kind of like people in that sense, where when they are unstable, they want to become stable. So we could think of the stability as kind of what atoms are trying to become. Real quick note here before we go any further. Radiation is not, I want to clarify, it is not a chemical reaction, because it happens within the nucleus of the atom. We're going to start talking about chemical reactions later in the year, and those happen between separate atoms. But radiation happens within the nucleus of the atom, so it's something completely different. So what we have here is a graph with our protons on the x-axis and neutrons on the y-axis. And what I did was I plotted some stable atoms as red dots here. And you can see they all fit into this kind of line area, which we call the band of stability. So I drew that in green. And if an atom falls within that band, we're going to consider that a stable atom. So to review, atoms are unstable when they have too many or too few neutrons, or they have over 82 protons. Because you remember the neutrons kind of act like the glue, and the protons have positive charges, so they want to push each other apart. And once you have 83 or more protons, no matter how many neutrons you have holding it together, the protons will want to push themselves apart more and it won't be stable. So when we have an atom with more than 82 protons, we have a problem. So if our problem is our nucleus of the atom has too many protons, greater than 82, it will want to go through radioactive decay to become stable. So the type of radioactive decay that this will go through is called alpha decay. And alpha decay is where the nucleus, so remember all these decays or radiation occurs in the nucleus of the atom. The nucleus will release 2 protons and 2 neutrons. So the way we can write this is we could write it like an alpha particle, like that, just a Greek letter alpha, or we can write it like this, because this is basically the nucleus of a helium atom with 2 protons and a mass number of 4. So that is what alpha decay is. And you can see how by going through alpha decay, this nucleus is losing some of its protons. And by losing its protons, it will be shifting closer to the band of stability. So that's why it's going to want to go through alpha decay if it has more than 82 protons. So we can also fall out of our band of stability if we're up here. What if we have too many neutrons and not enough protons? So if we have too many neutrons and not enough protons, that atom is unstable as well, and it will also go through a type of radiation or radioactive decay. But in this case, alpha decay won't help because we don't have enough protons. So by getting rid of protons, that wouldn't be helping us get closer to our band of stability. So we'll go through a different type of radioactive decay. This is called beta decay. And what happens in beta decay is, again, this happens in our nucleus of our atom. We have a neutron, and this neutron turns into a proton and shoots out an electron. And the way we could think about this is we start off with a neutron. Let me get another pen. You start off with a neutron, and it becomes a proton and an electron. So the charge is the same. So you balance the charge out on both sides. The charge hasn't changed. We haven't created any charges or lost any charges. And the mass is basically the same as well, because electrons have extremely small masses and protons and neutrons have very similar masses. So what we have here is our neutron becoming a proton, and it shoots off a very high energy electron that's speeding off, and it's not part of the atom anymore, so it's just shooting it off. So we write beta decay like this, or it can be written like that. And that would be if we had too many neutrons and not enough protons. So that would be if we fell on this part of our graph. And I'll write that down. Too many neutrons, not enough protons. So then you can imagine the other part that will have a problem is if we're down here. What if we have too many protons and not enough neutrons to hold them together? So in this area down here, we have this problem. Too many protons, not enough neutrons. So in this case, what we have going on is positron emission. So this is very, very similar to beta decay, except instead of emitting a positive or a negative electron, we emit a particle very similar to an electron, but it has a positive charge. So our proton becomes a neutron, and a positron, which is basically, you could think of that as a positively charged electron, and it shoots it off as radiation. So if we wanted to write the equation for this, it'd be a proton turns into a neutron plus a positron. So you can see on both sides of this equation, we have a single plus charge, and our masses balance out as well, because electrons have extremely small masses and positrons have the same masses as electrons. So extremely small mass, and then neutron and proton have very similar masses of 1 AMU. So our masses are about the same and our charges are the same on both sides. And just like with our beta decay, we have another way we could write this. You could write positron like this, or you can write positron with a beta sign. So with this problem, the nucleus has too many protons and not enough neutrons. There is also another way that the atom can solve this problem and become stable. So positron emission is one way. Another thing that the atom can do is something called electron capture. And this is where a nearby electron that's close to the nucleus gets grabbed up by the proton and those charges neutralize, and that proton becomes a neutron then, and it emits electromagnetic radiation, either as an X-ray or as a gamma ray. So if we wanted to write out what happens in this scenario, we have an electron, and it gets captured by a proton, and that neutralizes it, turns it into a neutron, and gamma radiation. Electromagnetic radiation, like gamma rays, they don't have any mass at all. They're just high energy radiation. So I don't need you might be confused. You might say, how do I know whether positron emission happens or electron capture happens? In this class, you don't need to know when one of them happens or the other one happens. You just need to know that these are both solutions for this problem that we have here when we have too many protons and not enough neutrons to keep them all together.